All right, this is the second hour of Physics 1B, section 1377 for the 15th, so it is? Yeah, September 15th. And we are now going to be discussing Bernoullis Principle, or Bernoullis equation. I'm reminded of a video that I will probably show to you all at some point, maybe tonight. If we can finish up the two problems that I want to do, I'll show you this video. I didn't know this, but so I think when we say Bernoullis Principle, I believe we're talking about Jacob Bernoulli. But the Bernoullis apparently were a very fascinating family, a lot of very, very intelligent people. Just remember hearing that on a YouTube video that had a lot of physics demos in it. Anyway, so Bernoullis Principle. I'm going to write down kind of in general what I want you to take away from this, just to start off, and then I'll try to prove it to you afterwards. Okay? So, in general, what Bernoullis Principle is going to state conceptually is that fast-moving fluids exert less pressure. That's ultimately what I want to prove to you. Okay? But that's effectively what Bernoullis Principle is going to state, is that fast-moving fluids exert less pressure. And at the core of this principle is how do airplanes fly? Why am I looking at my second monitor? How do airplanes fly? Why do balls curve? And when I say balls, I mean if you play baseball, curve balls. If you play tennis, you know how with a tennis serve you can... yes, Louis, the mass flow rate's always the same. It's not going to change if it's an incompressible fluid. If you play tennis, you know, when you serve golf, yes, Apoyan, definitely a good example. Golf balls curve like crazy, right? You know, I mean, if you ever watch golf on TV, especially these days, they put these nice little tracers so you can kind of see the arc of how the balls fly. And if you've ever tried to hit a golf ball before, you know it's actually really, really hard to hit it straight. I mean, putting is one thing, but if you try to take a driver and hit a ball straight, it's really hard. It's extremely hard. Anyway, yeah, so golf balls, tennis balls, when you're serving a tennis ball, you know, sometimes you'll put a ton of top spin on it or a ton of side spin on it to make the ball curve through the air. Tennis balls do a really good job of this because they have all those little hairs, right? Tennis balls, you know, think of a green tennis ball. They're really hairy, right? And all those little hairs actually help them to spin really well in the air. Plus, they're pretty light. So, Bernoullis Principle hopefully will help us to explain that, as well as something else. So I want to use a kind of a, I don't know, is this a thought experiment? It's not a thought experiment. This is more of a description of something you may or may not have experienced in your life. So let's say you're sitting at a red light, okay? So let's say that there's two lanes. There's two lanes, and you're sitting right here at a red light, okay? And what you're doing is you're getting ready to turn left, okay? So you've got your blinker on. You want to make a turn like this, okay? But, you know, you're sitting there, right? And probably there's some cars coming from this direction. There's probably cars coming this way, right? You know, you're in the right lane, you want to go left, but there's cars coming this direction. And what I want you to think about is what happens if there is a very large truck, okay? So back here, let's say there's a very large truck. And that truck is driving. And let's say it's like a big, like, either like a semi or like a big, like, budget rental car or something like that. Not budget, sorry. Like a moving truck, right? Basically one that has really high, wide walls on the side, okay? So a semi is a perfectly good example. And let's say that this truck comes speeding by here, and let's say it has a velocity of, like, let's say it's a normal street. So maybe it's moving fast, but not, like, crazy fast. Let's say it's moving with the velocity of 40 miles an hour in this direction. And it comes very close to you, okay? So eventually that truck is going to pass by you, yeah? So what I want you to tell me, if anybody remembers this, so as this truck moves in this direction, right, and eventually reaches this point right here, what do you notice happens to your car as the truck drives by? It shakes? Any other answers? What do you all notice? It leans toward the truck? It vibrates? Okay, anyone else have an experience with this? I agree with Jacob. I feel my car basically be almost sucked into the truck for a second. as the truck flies by, and then immediately your car will start shaking afterwards, right? Because if your car gets pulled off of its equilibrium position, it's going to obviously rock back and forth until it stabilizes, right? Yeah, your car is actually going to be almost attracted to the truck as it passes by. It's basically your car is going to feel a force that's going to draw it to the truck, okay? And let me see if I can't give you a reason as to why that would be the case. So first of all, you have to just accept that what I told you here is true. The fast-moving fluids exert less pressure. And then we combine that with Bernoullis equation. So think about the air that's surrounding this region right here, right? So there's going to be air, right? And so let's say we have some streamlines of air right here, right? This is the air. What do you think happens to that air as it tries to squeeze into this little region right here? Yeah, this is something that you may not have noticed before, but I promise you, if you pay attention the next time you're sitting at a stop sign and there's cars that are passing you like this, I guarantee you will feel it. It is very hard not to notice. It gets sucked in like a vacuum, yeah. Okay, yeah, but I mean, what's happening to the airspeed here in between? So you got the air out here, it's flowing at some speed, right? What happens to the air as it goes into this little wind tunnel right here? It gets speeds up. That's what we just learned, right? That when you have a constriction, the air here is going to be moving really fast, right? As a result, what's going to happen is that in between these two objects, the pressure is going to be low. So this is going to be low pressure out over here. On the outside of the truck, on the outside of your car on this side, you're going to have higher pressure. Just because it's normal pressure. This would be normal pressure. This would be atmospheric pressure. But when you have a pressure imbalance, right, then that little region in between the truck and the car acts like a vacuum, and now there's a force exerted on your car in this direction that sucks it toward the truck. And that is basically what Bernoullis Principle does. Is it makes it so that fast flowing fluids allow things to feel forces. To give you another example, let's talk about airplanes because we might as well. Airplane wings, if you look at a cross section of an airplane wing, okay, it kind of looks something like this. Now, I don't fully understand how this works. I really don't. Somehow, the shape of the plane wing has the effect that as the air comes through, the air on top moves faster than the air on bottom. So the effect of this wing shape is that when the wing starts to move, the streamlines somehow move faster over the top. The air flows faster over the top, and somehow it gets kind of slower across the bottom. Which means, on top you're going to have the low pressure side. On the bottom you have higher pressure. And the effect of that is you get an effect called lift. And I believe that it tends to kind of go up at an angle. You get this force that we call lift. That's basically how an airplane flies. Off of Bernoullis Principle. That as you push the plane into the air, the shape of this is just, I mean, if you really, oh yeah, that's the other thing. What Louis said is right. So this one you can actually do yourself, and I'll show you too. Here, let me turn my light on. So you can all do, I don't know if you can still hear me. You can all do this. What you can do is you can take any piece of paper, preferably something that's kind of light, not too heavy. You don't want to use construction paper, as if anyone actually has it. And what you can do, okay, is you can take a piece of paper, and what I'm going to do is I'm going to put my lower lip on top of the paper, just to prove that I'm not blowing underneath it. And I'm just going to blow air straight across right here, right? And if what I'm telling you is true, when I blow air straight across in this direction, it should be high-speed air, which should allow this page to move straight up. So let's see if we can do it. And if I don't blow very fast, the effect won't be nearly as high. But you still see it start to pull up. And when I blow really hard, you'll see the effect is huge. it just immediately flops out like that, right? Which I think is pretty cool. You should try it yourself. Tell me if you can make it work in the chat. Someone showed me that demo, I think, one of the first days that I was teaching Physics 2A. It was like first semester I was even here. And this full-timer who had been around for a long time, her name was Susana Prieto. I sincerely doubt any of you know who that person is, but she was here a few years back. She was still teaching here. And yeah, she showed me that demo, and I was like, oh my god, that's so simple. Anyone can just do this. So I'm glad you mentioned that, Louis, because I almost forgot to show you that to you. I showed it to my other class, but I just forgot. So that's Bernoullis Principle, basically. That's the conceptual idea, and now we want to come up with some math to describe how it works. It turns out that the equation that we're gonna derive for this is basically going to be a work-energy equation. So we're going to use work and energy to come up with an equation that describes this phenomenon that we just described. So that's the principle. Fast-moving fluids exert less pressure. And for those of you that haven't had lab yet, when we have lab, I will show you a couple demos with this. I didn't actually manage to do that with the first group that came in the lab. I think largely because I was focused more on doing the lab. But next time the group that was on Monday is in the lab, I'll show you some demos with this too. We also hadn't talked about it yet, so. Okay, so Bernoullis equation. Now for this one, we're going to have a very similar type of setup to what we had before. So we're going to have a tube. It's going to have some cross-sectional area here, A1. And it's going to the tube is going to get smaller, just as it did before. But in addition, the height of the tube is also going to change. So now our tube is going to look something like this. Okay, so not only does the cross-sectional area change, but also the altitude is going to change. So I'm going to call the height of the center of my tube over here, I'm going to call that Y1. And I'm going to call the height of the center of my tube over here Y2. And then we're just going to kind of look at a packet of fluid as it flows through here again and talk about what happens to it. So over here we start off by drawing our packet of fluid. So here's some fluid flowing through our pipe. It's flowing at this point with this velocity that we're going to call V1. Okay. When it gets up to this position here, we know from what we talked about with the continuity equation that it's going to end up, if it's an incompressible fluid, it's going to end up occupying less volume, or sorry, not less volume, the same volume when it gets to here, but it's going to stretch out a little bit. At this point, we'll say the velocity of the fluid is going to be V2, and the fluid has a density, and we also are going to have to label this piece right here. This time I'm just going to call this delta x1, and over here I'm going to call this one delta x2. I don't even know if we need those distances for this part. Now, one other thing that I'm going to put on here is I'm going to say this pipe, it continues in this direction, and it continues in this direction too, okay? Which means that there's fluid back here, and there's also fluid up here. And as our packet of fluid that we've traced through our system right here, remember it's the same packet of fluid. As it flows through here, it's not free to flow completely because there's fluid in front of it, right? You know, as this water tries to flow through here, there's also fluid in front. And that fluid is going to exert a pressure backwards on the fluid. In addition, there's fluid back here that's behind it, and that fluid is going to exert a pressure that's forward. So what I'm going to say over here is that this fluid is going to be exerting a pressure on our packet that I'm going to call P1. And up here, we're going to say that on this portion of the fluid, because it's trying to push into the fluid in front of it, there's going to be a backwards pressure that we're going to call P2. Does that make sense? One way you can think about it is, if it doesn't make sense, imagine that I have a tube, okay? And let's say it has the same shape everywhere. And let's say this tube is filled up with beads, okay? And these beads are free to flow through this tube. I can think of some toys that I've seen that are kind of like this. So this tube is filled up with beads, right? Okay. Now, suppose that I want to track what's happening to a bead like right here. So I'm interested in just this one bead, okay? And someone pushes on this direction here, right? If you push this way, then this bead, obviously, will feel pressure from the beads behind it, right? And that'll make it move forwards. But it's also going to feel backwards pressure from the things in front of it, right? After all, if I hit this one, it's going to make this one move, and this one, and then this one, but then that one's going to hit the one in front of it, so it's not going to move as fast as if it was just free to flow through the tube, right? So you have to take into account the stuff from behind and the stuff in front. And that's why I say that we care about the pressure of the fluid from behind, and we also care about the pressure that's pushing back from the front. Does that make sense? Does anyone have any questions before we go through the math? Okay. So now what we're going to do is we're going to talk about the work that's done on a packet of fluid. Does anyone remember how you calculate work? You're going to have to help me because I don't remember. How do you calculate work? Just in general. I don't need like an exact. Force times distance, exactly. To find work, we need a force multiplied by a distance. F times delta x, okay? But we know that if you have some pressure, P1, that's exerted on an area, that there's going to be a force. And how big is the force going to be? What will the force acting on this side over here be? You got it. It's almost right, but its pressure is force over area, so force is pressure times area. So if I take P1 times A1, that's going to be the force on the backside. And if for P2, the force over here on the front, we're going to call F2. And F2 is going to be equal to P2A2. All right. So the net work, or the total work, is going to be equal to F1 times delta x1 minus F2 times delta x2. And I say negative here because the pressure of the fluid in front of us is doing work against us, while the pressure from the fluid behind us is actually helping us to move that packet along, right? If we plug in what the values of these things are, we get F1 times delta x1, which is P1. Oh, whoops, sorry. No, that's all right. We get F1, which is P1A1, pressure times area. We multiply that by delta x1. F2 is P2A2, and do delta x2. And the reason why we're multiplying by these distances is in order for the fluid on the left to move, it needs to move across this distance. If it started here, if, say, the right edge started right here, it would need to move this distance to get across this section. And over here, you got to move a little bit farther of a distance of delta x2. That's why we're using this. But hey, A1 times delta x1, what's that equal to? What is the area times the distance equal to in our picture? Volume, yeah? So we can write this as P1 times volume minus P2 times volume. And the volume should stay the same. I'll just write that up here, that if I take A1 times delta x1, that's going to be the volume of our packet. But remember, we're talking about incompressible fluid after all. So as long as we're looking at the same packet of fluid, it has to have exactly the same volume, right? That's what incompressible basically means. That's what I said at the beginning of class, is incompressible means the volume can't change, right? So if we know they have the same volume, now we have this
really kind of a nice simple expression of pressure times volume minus pressure times volume. And I will tell you that we're going to see pressure times volume be related to work quite a bit in this class, especially as we move into talking about thermodynamics. And you may remember an equation that you learned in your chemistry classes where pressure times volume shows up as well, right? The ideal gas law. And we'll see that work is connected to these quantities in this class too. Anyway, so that's the work done on the object. But work, if you remember what work is, the definition of work, or a definition of work, is the ability to, no, that's the definition of energy. Definition of work is when you do work on a system, it can either increase or decrease the energy of the system. When you do positive work, you raise the energy. Simple example, if I take an object and I exert a force upwards on it, I increase its gravitational energy. I do work and its gravitational energy goes up, right? So there's a connection between work and energy, and that connection is given by our energy equation, which says that the work done by non-conservative forces is equal to the change in kinetic energy of a system plus the change in potential energy. And if you'll remember from your Physics 1A class, kinetic energy is 1/2 mv squared. So in this case, the change in energy is going to be 1/2 m times v2 squared minus v1 squared. And the change in potential energy, because we went from a height y1 to y2, is going to be the mass of our packet times g multiplied by y2 minus y1. And the work done by non-conservative forces is going to be the same as this. So the left-hand side of our equation is going to be P1V minus P2V. These are V's. To distinguish between volume and velocity, let's put some little bars on top here. So that's a nice expression. It involves pressure and velocity, and it directly connects it to the velocity of the fluid and the height of the fluid, right? What we can do now, though, is we can say, you know what, when I'm talking about fluid flowing through a pipe, I don't really ever know what the mass is, you know? You can't realistically do what we're doing here. You can't like draw lines on the pipe and say, I want to look at just this one piece of fluid, because that's just not how fluids work. In general, we don't talk about the mass of a fluid. Instead, we talk about density, right? Density is a lot easier to talk about because the density is the same throughout it. So what we can do is we can divide the entire expression by the volume, and what we'll get is density on the right-hand side. So the left-hand side now is going to be P1 minus P2, and that's going to be equal to 1/2 m over v, that's density, right? Mass over volume. And m over v again, once again, that's density. Right? Scrolling down a little bit here, I'm going to put all the ones on the same side of the equation, so I'm going to rewrite it like this. And then we'll put all the 2's on the right-hand side of the equation, so I'll add P2 to the right. And this is Bernoullis' equation. It says that if you take the pressure of your fluid and you add to it 1/2 rho times the velocity of the fluid at that point squared, kind of like, it's not really kinetic energy, it's more like kinetic energy per unit volume, but it's still kinetic energy. And then we have rho, and you have to add to that the density times g times the height. This is Bernoullis' equation. And we can write it in an even more general form to say that if I know the pressure at a point in the fluid, and I know the velocity at that same location, and I also know the elevation relative to some fixed point, that this entire summation here, pressure plus 1/2 rho v squared plus rho gy, this is constant in a fluid. And that's Bernoullis' equation. Does anyone have any questions? Well, the reason why it's constant is, if you look at this equation right here, it says, P1 plus 1/2 rho V1 plus, etc. Notice that this is at one location, right? It's not like the 2's and the 1's are mixed. It's pressure at point 1, that's right here. Velocity at point 1, also right here. And elevation at point 1, also right here. So they're saying at this point in the fluid, the summation of pressure plus this quantity is equal to the same expression at another point in the fluid. So what about at a third point? Have to be the same, right? At a fourth point, it has to be the same. So in general, basically just that quantity, has to be a constant. Just like with the continuity equation, area times velocity is also constant. In fact, you're going to be using the continuity equation in tandem with this, because after all, if you know, let's go back and look at our picture right here. If I know the velocity 1, and I know area 1, and I know area 2, I can find velocity 2, right? They're connected to each other. V2 and V1 are connected to each other, right? So very commonly in problems, you'll see immediately that you'll have to use them together. Now let's see if I can get back to the concept, because that equation doesn't immediately jump out and tell me that this is true. So let's see why fast-moving fluids exert less pressure. So when I look at just that expression right there, right? Let's say that I want to apply it to a certain type of a system. And let's not worry about elevation for now, okay? Let's just say that I have a fluid, it's in a pipe, right? And the pipe condenses down like this. So it starts off with this kind of big cross-sectional area over here, and eventually it opens up over here, right? We've got fluids flowing through here, right? And I tell you that the height on this point and this point are the same, right? So we have the same elevation. We'll call this y2, we'll call this y1, and just say this is the same elevation here, all the way through. So if y1 equals y2. Then we just have to worry about this portion of the equation. So the quantity, pressure plus 1/2 rho v squared would now end up being, this is now a constant. Okay. So if I tell you the pressure right here is P1, and the pressure right here is P2, how are they going to compare to each other? Well, we know that the velocity in this section, if we call it V1, is going to be way slower than the velocity in this section right here, right? So if the velocity goes up and the density stays constant, what has to happen to the pressure in order to make it constant? If the velocity goes up, what has to happen to the pressure if we want this expression to be constant? It has to go down, right? So that's why when the velocity goes higher, the pressure goes down. i.e., fast-moving fluids exert less pressure. If this is fast, then this is going to be low. If it's slow, then the pressure is going to be high. Can you all see that from the equation? Also, notice that because the velocity is squared, this effect is very, very noticeable. And what I mean by that is that when the velocity is squared, if the velocity doubles, then the pressure has to increase by quite a bit. Because doubling the velocity makes this term increase by a factor of 4, right? So if this term gets 4 times as big as it was, this is going to have to get a lot smaller to compensate for that. I'm not going to say that it needs to be a quarter as big. It's not that simple, but that's generally the idea.
Okay. Are y'all ready to do some problems? I've got 2 problems that we can do here. I think they're pulled pretty decent. This was supposed to be the picture for this one. I'll leave it here in the notes. I'll put it down here with the derivation that we did, but that was the picture I took from another textbook. I decided to draw my own picture, though. Okay. Speed of efflux, I don't know how to pronounce that. So this problem is a symbolic problem, but we're going to put numbers in. All right.
Figure 12.25 shows a gasoline storage tank with a cross-sectional area A1, up here at the top, filled to a depth h. The space above the gasoline container contains air at pressure P0. That's not atmospheric pressure. I don't know why they do this in this problem. I hate this. Because the book uses P0 for atmospheric pressure all the time, but then look down here. Now they're using P atmosphere all of a sudden. I don't understand this book at all, but whatever. It's a good problem, so we're going to go with it. Pressure at the top is P0. That means that this is a pressurized tank. Okay. Does high blood pressure mean a slower flow of blood? That's a great question. It seems like that would be the case, right? Not just because of this, but just... I'm thinking about, like, if you get, like, a constriction somewhere in one of your arteries or something like that, the pressure is going to build up, basically, right? Do you have, like, a constriction? I don't know. That's a good question. Let's get back to this problem, but let's come back and talk about that later. Because the flow of your blood has to be kind of very similar to these kind of things that we're describing here, because your blood is basically flowing through little tubes, right? Your veins and your arteries. Okay. So, space above the gasoline contains air at pressure P0. So this is pressurized. And what I'm going to say in this problem is we're going to let P0 be equal to 1.5 atmospheres. Okay. The gasoline flows at the bottom of the tank through a short pipe with a cross-sectional area A2. So that's down here, A2. So you got this pipe at the bottom. We want to derive expressions for the flow speed in the pipe and the volume flow rate. Okay. The flow speed in the pipe and the volume flow rate. So what I'm going to do on here is I'm going to say that at the top, the velocity of the fluid is going to be V1. And at the bottom, when it flows out here, the velocity is going to be V2. We can see that there's a height right here. I'm going to define the point down here at the bottom to be Y2. I'm just going to say Y2 is equal to 0. I'm going to define the point at the top right here to be Y1. We're going to say Y1 is equal to H. We're also going to pick a number for H. Let's say that H is equal to, let's say 3 meters. Okay. Oh, by the way, Bernoullis equation also talks about what happens as a fluid's speed increases due to gravity. But I don't think it's too surprising to you all that a fluid flowing downhill will pick up speed and a fluid flowing uphill will slow down. But that's also included within Bernoullis equation. Okay, height, 3.53 meters. Pressure naught is 1.5 atmospheres. At the bottom down here, the pressure is PATM. So we're going to call, we'll just call it PATM. The pressure of the atmosphere is 1 atmosphere. What else do we need to know to solve this problem? I guess the other information we need to know is what A1 and A2 are. So let's say that the radius of our tank up here at the top, let's say R1. How big are these kind of tanks? So if you see a big gas tank on the side of the road or something like that, like a big gas container, it should be pretty big. It should be like maybe, maybe 5 meters across. Maybe that's too much. I don't really know. And then let's say A2 down here is quite a bit smaller. So let's say that the radius of the bottom, I don't know how to draw this on here. Here, we'll just draw it. So let's say the radius right here, we'll call it R2. And let's set that one equal to, it's got to be a lot smaller. Let's say R2 is like 10 cm. Okay, I'll put this over here. So R1 is 5 meters. That's the area, the radius at the top. We're going to say R2 is 10 centimeters. Do we need anything else? Okay, if we need another piece of information, I'm going to pick a value for it, but I do not think we need any other information other than that. Okay, so let's apply Bernoullis equation to calculate these things. Our goal is to find this velocity and the volume flow rate. So mostly just we're going to find this velocity. So that's our goal. Solve for this. I guess I can start over here. It feels like there's not enough room though. Yeah, let's start over here. So let's start with the Bernoullis equation. P1 plus 1/2 density times V1 squared plus, we're going to need the density of gasoline. Can anyone look that up for me real quick while I'm writing this stuff out? Can someone go look up the density of gasoline for me? So P1 plus 1/2 rho V1 squared plus rho GY1 is going to be equal to pressure 2 plus 1/2 rho V2 squared. Thanks, Louis. So it's less dense than water. It's interesting. Yeah, it's definitely going to vary. It's going to depend on what kind of gasoline you're talking about. But as long as we got some number to work with, that works for me. All right, there is the Bernoulli equation. And now we want to basically kind of start plugging information in that we know. I'm not going to plug variables in until the very end, but we do want to kind of plug some things in here. So the first thing we know is that y2 is 0. And that's the only thing that's 0. We're trying to solve for velocity, so the next step that I'm going to do is I'm just going to rearrange our equation until only the velocity shows up on one side. So we'll subtract p2 to the left side, and then we'll leave rho gy1 on there. And we're just going to move both of the terms that involve a velocity to the right-hand side and do some factoring. How are we doing on time? I think we have plenty of time left. Yeah, we do. So hopefully we'll have time to do both these problems, which I didn't get to in the other class. All right, so this is our equation now. All I've done is subtract 1/2 rho v1 squared to the right-hand side. So it shows up over here now. I factored out 1/2 rho because that term and that term both have 1/2 rho in it. So the narrow pair is this combined term right here. And everything else has been moved to the left-hand side because we know all this information. Now, in our problem, our P1 is this one, and our P2 is this one. Okay? So, how many unknowns do I have in this problem right now? How many unknowns? When you look at that equation right there. V2 is an unknown. What else? Do we know all the other? V1, yeah. The two velocities are both unknown, right? So as it stands, there's no point in continuing with this equation unless we can come up with another equation that relates the velocities, right? What equation relates the velocities to each other? The continuity equation, yeah. A1 V1 equals A2 V2, exactly. You're always going to have to do that with these type of problems, okay? Sometimes there's going to be little tricks that I'll tell you in a second, but the other piece of information we know is that A1 times V1 equals A2 times V2, which means that we can eliminate V1 in favor of V2, because V1 is going to be equal to V2 times A2 over A1. If we plug that into our equation up here, we're going to get this. Let's go ahead and replace P1 we said was P naught. I hate that. And P2 we said was P atmosphere. We're getting to a point when I'm going to need to scooch down a little bit in order to fit all this stuff in. So we're going to come down here. So we're going from this line all the way down to that line. So P naught minus P atmosphere plus rho gy1. On the right-hand side, we have 1/2 rho. V2 squared isn't going to change. And now for V1 squared, we're going to plug this in. And we'll just square it. Need to make a little more room so that minus sign doesn't get, then we just have to square this. Okay, so we're plugging in for V1 with this expression. And now we have just one unknown. Factor out the V2 squared. You know what? I think you all will follow along just fine if I do the following. There's a 1/2 here, right? So let's multiply the 1/2 to the left-hand side. And let's divide by rho. Let's get rid of that right there. And then let's factor a v2 out. Okay. Does that look good, everyone? Okay. So now, I think we can solve, but let's get everything together first. So we're going to have 2 over rho times P naught minus P atmosphere plus rho g y1. We now need to divide by 1 minus a2 squared over a1 squared. And that all should be equal to v1 squared, which we can then square root both sides. Oops. We can square root both sides here. And that will give us our answer. We'll have to plug everything in, of course. And that's not v1. Nope, that's v2. All right, before we start plugging the numbers in, does this make sense to everyone? Okay. So let's go through and plug our numbers in. So we're going to have square root of 2 over rho, which we said we were going to use 800. Okay, I can't write that low on the screen without it looking like crap, so we're gonna start over again. Let's just write 2 over 800. That's the density. This multiplied by P naught was the pressure at the top. Remember, this tank was pressurized, and we said that the pressure at the top was 1.5 atmospheres, right? Yeah, we gotta convert that, don't we? Well, 1.5 atmospheres is going to be about 1.5 times 10 to the 5 pascals. Okay, so we're going to say P naught is 1.5 times 10 to the 5 pascals. And we're going to say P atmosphere, we're just going to use kind of rough numbers for this one, is going to be 1 times 10 to the 5 pascals. I know that it's a little bit more than that, but we're not going to make much of an error by making that. So then P atmosphere goes next. So we have that minus 1 times 10 to the 5th pascals. Okay, plus rho g y1, so that's going to be 800. I think we said that y1 was 3 meters. Yeah. We said the height was 3 meters. And y1 is equal to the height right here. So we have 3 meters right here. And then we need to divide all of this by 1 minus a2 squared over a1 squared. I believe we said that R2, which is the one at the bottom, had a radius of 10 centimeters. Yeah, and R1 was 5 meters. So let's write this down here. So R2 is 10 centimeters, which is 0.1 meters? And R1 has a radius of 5 meters. So the top is huge. The bottom is much, much smaller, right? Is that what I said? Yeah, R1's 5 meters. Oh, I left off gravity, thank you. So there's also a G right here. Thank you so much. So this is 9.8 meters per second squared. We don't make it negative, we just leave it positive like that. Okay. The denominator we have a2 squared over a1 squared. So the area of a circle is pi times r squared. So if we plug in for a2, we're going to use r2, which is 0.1. And that whole thing is going to be squared. And we're going to divide that by pi times r1, which is 5 meters. That whole thing gets squared. And then this whole thing, we have to square root everything. And this should be equal to v2. Pretty much everything got on the screen there. You're not missing anything. A little bit got cut off, but it's nothing important. Just that bracket, basically, right there is getting cut off. Is anything getting cut off on the... No, it's fine. So there's our equation, and we're going to calculate it. But before we calculate it, I want you to look at this piece right here. I want you to just calculate that. The pi's will obviously cancel, right? 0.1 over 5 is like 1 divided by 50, right? When you square 1 divided by 50, what you're going to get is 1 over 50 times 50, which is 2,500, right? What do you get when you do 1 minus 2,500? Well, that's easy. You get 2,499 over 2,500, right? You plug that into your calculator, you're going to get something like 0.998, I bet. What do you get if you plug that in your calculator? It's going to be super close to 1. That's my point. If you do 2,499, you divide by 2,500, you get 0.9996. Which is approximately equal to 1, right? So this expression down here, right, this whole thing is equal to that. Which means if you were to just put in 1, you really wouldn't make much of an error, right? You're square rooting it too, which when you square root it, I bet it's even closer to 1 because you square root it right here, right? And then it's going to be 0.998. The square root of this is 0.998. So, yeah, my point is this. Like, a lot of these problems, what's going to happen when you're doing them, okay, is you will be given all of the pieces of information that I gave you except for this one right here. When you have problems like this with these tanks, okay, sometimes what will happen is they will not give you this radius, okay? And you're going to have to make an assumption. You're going to have to make an assumption that if they tell you there is a small opening at the bottom, and you can tell in the picture that there's a wide opening at the top, you know that the fluid at the top is going to be flowing super slow compared to the fluid at the bottom, right? And so the assumption you're going to have to make is that the velocity at the top is 0. Does that make sense? And had we made that choice in our equation here, had we assumed that v1 was 0, then this expression would have been 1 or 0, which means this would have been 0, which means we basically would have just been dividing by 1, right? Did you all follow that explanation? If they do not give you the radius of a tank, and you can see in the problem that the tank is huge, and at some other point in the problem you have a small outlet, right? Then the assumption that you are going to have to make is that the velocity at the top is very small relative to the velocity at the bottom, and therefore that you can treat it as negligible. Y'all got it? Does that make sense? And you'll make a very small error. In fact, what we can do here is I'll have you all calculate this expression twice. So basically calculate it once and, include everything, and then calculate it again and set that term equal to 0 and see if you get the same answer. You're going to get basically the exact same answer. All right, so calculate V2 for me. Since this is a pretty long calculation, I'll pull up the calculator from the internet. I really like this calculator. It's quite nice. Okay, so here, let's squeeze this down so we can get it all on the screen. Okay, so that's the calculation we're doing right there, right? So we need a square root. Square root. Close the parenthesis and then start writing inside. All right, so we've got 2 divided by 800 times 1.5 times 10 to the 5, or 1.5 E5 minus 1 E5. The E basically means times 10 to the, I'm sure you all know, a lot of you know, plus 800 times 3 times 9.8. And we're going to divide by 1 minus, I'm going to go ahead and cancel out the pi, so I'm just going to do 0.1 over 5. So 1 minus, we'll just write 0.1 divided by 5, and then we'll square that. Let's check to see that we did it right, because it's easy to make mistakes here. Square root of 2 divided by 800, that's on the outside, open parenthesis, times 1.5 times 10 to the 5th minus 1 times 10 to the 5th plus 800 times 3 times 9.8. So that's the numerator. We divide that by all of this, which is 1 minus 0.1 over 5 squared, and then a closed parenthesis. I think that should work. So we get 13.56 as our answer for V2. We'll just call it 13.6 meters per second. Anyone have any questions? Now, if instead I just divide by 1, notice that the answer that you get is the exact same number out to 4 digits, which means that it would be almost an immeasurable difference between these two calculations, right? So just to reiterate what I was saying earlier, if you don't know what the area of this thing up here is, that's okay. That actually means the problem's easier than you thought it was, because that means that you get to assume one of the velocities is 0. Very common thing you're going to see show up in these type of problems. I don't know if it shows up in the next problem we're going to do, but very, very common thing. Okay, so let me zoom out a little bit so we can look at it all together. Does anyone have any questions about what we just did there? You'll see a lot of these on your homework. The problems really aren't that hard. I mean, they can get tricky, but usually what's tricky about them is they expect you to make assumptions, you know, and I hope that I can share with you as we do these problems some of the assumptions you're going to need to make as you're doing it. Do they want us to find mass flow rate too? The volume flow rate. Yeah, they want us to find the volume flow rate. Well, the volume flow rate is going to be the area times the velocity, right? So if I want to find the volume flow rate, which we said before was dv dt, then I just need to take like a2 v2, right? Which would be a2 was pi times 0.1 meters squared, and we would multiply that by v2, which we just calculated to be about 13.6 meters per second, right? So the volume flow rate would be 0.427 meters cubed per second, which would actually be, that's a big number, 427 liters per second, right? That's a lot of liters. All right. How many liters are in a gallon? It's like 1.5? 2? It's got to be at least 2, right? Gotta be at least 2 liters in a gallon, right? Is it 4? Less than 4? On the order 4? Okay. Alrighty, so let's do one more problem. I could show you this video instead of doing a problem. I don't think it's even remotely possible we can finish this problem in 10 minutes, unless I just go really, really fast. Do y'all want to watch a video instead? I want to show you this video of all these demos, since we haven't really been able to see a lot of these demos. Let's see if I can find the one I was talking about. I found one from a professor. This is it. Yep. This is just about long enough. This dude is an El Camino professor. I don't know if he was an El Camino professor. I think he was, though, at one point. I'm pretty sure. This video is old, by the way, but I don't think that makes it bad. I believe in order to hear the sound, I need to switch my screen. I have to change windows. We're gonna go a little over with this, but I think that's okay. If you need to go, you can always. I'll put the link down here in the bottom. That way, you can watch it yourself later if you want to. So if you feel like leaving, then you can you can go, but I'm going to go ahead and click the play button, and we'll just watch this as class ends. I'll stick around afterwards if you have any questions. You know what also? Just in case, I'm going to stop the recording right now.